Hi, everybody. Michael Shermer here, director of the Skeptics Society, the publisher of Skeptic magazine, the first of our brand new Science Salons. After 23 years at Caltech, we decided we'd try something new, make it a salon and a book party, so there's actually more books, which is good for authors and publishers and publicists, and great for all of us to have more intimacy with the speaker and author. And I was sort of inspired by the old Enlightenment salons of the 18th century, Voltaire and all these good folks.
That's who I was thinking of myself.
Yes, you are today's Voltaire, yes. And in the 19th century, there were a lot of public science evening events like this, including the Lunar Society of Birmingham, which was a group I often admired. They would meet on the first Monday after the full moon, because when they went home at midnight after many adult beverages on their carriages in the dark, the moon would light their way, so they were the Lunar Society of Birmingham. Well, we're not going to quite do that, because they didn't have the lawyers we have today to account for your drinking behavior. So, but we do have the format for today is Lisa and I will do an in conversation for a little while, then we'll turn it over to sort of a Q&A, but it can also be a dialogue. You could converse, and then we'll do our book signing. Everybody gets a book that's here. You already purchased one, and they're all in a stack over there, including extra copies of the latest issue of Skeptic magazine, which are also free. And then we'll have beverages and wine and food, and I got some shrimp, and I just went down to Whole Foods, and I just down in the cart, and so it was fun. And so and the wine is brought to you by this company. This is a Latier, a Merlot, very nice. So Michael McCarran up here is our wine sponsor.
I totally want a bottle of this. Oh my God.
Well, this is your bottle. This is for you. So MHM etching, this is what they do. They etch wine bottles for corporations and whoever wants, organizations and so on. So, and the wines that we have actually have your book cover on the back.
Oh
so
my God.
so we have one of those for you too. So we have a red and a white. Yes.
Fantastic.
So thank you, Michael.
And I'll mail it to you too, so you don't have to worry about it.
Thank you.
Yeah, Lisa's on a book tour.
This is. I'm really glad I have a great cover. It's so beautiful.
Yes, it's good for that. Yeah.
Nice.
And of course, I want to thank the Natives, David and Jackie, for letting us use their home. A beautiful architectural digest award-winning home. If you've seen, just look out for some commercials and films. You'll often see this house featured there. And do join us and them for their music concerts in the future. So without further ado, so our next event, the second one, is December 20th. I have Michelle Feynman, Richard Feynman's daughter, who's in charge of his estate and his papers, and she's put together a beautiful collection from Princeton University Press, the quotable Feynman, and he was very quotable. And so I also invited Leonard Mlodinow, the physicist, and Feynman's van. We have Feynman's van coming. It's parked down in South Pasadena in a garage by a guy named Seamus Blackie, who's a physicist that put up his own money to restore the van, which was recently featured on Big Bang Theory. And so I have Leonard coming to explain the Feynman diagrams on the side of the van, so you can get your picture taken and go, this one explains whatever it is, because I don't know it. At any rate, so our guest today is Dr. Lisa Randall. She's the theoretical physicist, Frank B. Baird Jr. Professor of Science, where she studies theoretical physics and cosmology at Harvard University. She's a member of the National Academy of Sciences, the American Philosophical Society, and the American Academy of Arts and Sciences, and she's the recipient of many awards and honorary degrees.
Yeah, skip that part.
Skip that part. Okay.
This is an old bio.
Always well, I know, but it's cool. I mean, It's cool. The most cited physicist up to at least 2007 anyway. I just want this one paper, Large Mass Hierarchy from Small Extra Dimensions, because I was this close to getting that published before you scooped up. But her previous books are Warp Passages and Knocking on Heaven's Door. She spoke for us at Caltech on the latter one. A terrific discussion on science and religion, which we'll get to later. And the new book is Dark Matter and the Dinosaurs, The Astounding Interconnectedness of the Universe. It's a beautiful book, beautifully designed, I'm still a fan of physical books. I think that's a good thing, even though I listen to this on the unabridged audio. Your reader is quite good. It's
I like
well
her.
done.
We kept her from the last book.
Yeah.
I
So I thought I'd start by just asking, because as a book author myself, I'm always curious, how do you work as a writer? I mean, there are writers that work from 8 to 12 every morning or whatever, and they're super disciplined, and then there's those like me that just catch as catch can. You work on the airplane in the Starbucks or whatever. And how did you write this book? How do you write?
I actually do write whenever I can, but I don't think that's necessarily less disciplined. I think I'm writing kind of all the time that it's available, and and when you add it up, it's quite a bit. And I actually like, being in beautiful places where I can just sit in my chair without feeling like I want to get up and walk around. I also like Amtrak for that reason. It's like there's no place to go, so you're in your seat. But I do sit at my desk and write too, obviously, or actually sit on my couch. I just like to be comfortable when I'm writing. So, but of course, sometimes you're researching, but just when I'm actually just editing, I just like to be someplace where I'm not thinking about other things, where I can really just focus. Because a lot of what I'm doing when I'm writing is, obviously there's the ideas themselves, but I usually have pretty broad canvas. So a lot of it, the editing is involved with tying in the ideas in a way that's coherent and, cutting things down so that you can get through it all.
Mm-hmm. So much of your previous books dealt with, relativity and quantum physics and so on. So I was surprised. The dark matter, of course, would be something a theoretical physicist would get into, but the dinosaurs. So as I started reading the book, I was astounded that it's about so much more than that. It's about, pretty much everything. So were you just feeling restless and think, I'd just do or did you just sort of stumble into it step by step?
Well, one of the reasons I wrote this book was because I realized I could tie together this big story. When you look at most books, they are about one particular part of the way of looking at the universe. And I thought it was worthwhile to put together the big story so people can see, how, especially since I work on, as you said, this elementary particle physics, it seems so removed, and to really show how these small particles tie into everything we see in our universe, and what are all the accidents or deliberate things, not deliberate, but in the sense of deliberate, as you know, but just what is determined by the physics, and what are accidents, and just how the things that we see today came about. And it really does make me look at the world differently. And when my friends read it, it's really rewarding when they say they do too, because you think about all that went into what we have here. And I think, especially today when we're thinking about what's happening to the planet, it's useful to have sort of that big history in mind. And it's just intrinsically interesting to just really just see how it all ties together. So I was actually enjoying the opportunity to, and for me, I learned a lot of things when I wrote this. The first section, as you know, is cosmology, the evolution of the universe, big question. But the second section really focuses on the solar system and comets and asteroids and what hits the Earth and life and how it's all connected. In this, literally, in the sense that some things come here and some things go out there.
Since you're dealing with impacts, I thought, wouldn't it be wild if, like, while we're sitting here, and a meteor came streaking through the window?
Well, but that's the hilarious story that I tell towards the end, where we were doing our research, and
yes.
I actually suggested to my collaborator that we think about this, and the next day there was
yes.
the explosion
the Russian
in Siberia. In Siberia. So we're like, okay, we have to do this.
I'm always curious, why is it that I always assume that they're coming in this way, but the impact craters look like they came straight
right.
in.
So actually, there's a whole chapter about impact craters, and because I also didn't know that. And actually, it's really interesting. I don't know if any of you have seen. I haven't actually seen it up close. The Barringer meteor crater in Arizona. There was a big a question at that time of how it was formed, and one of the things that confused people was precisely the fact that it was circular, because you would think if something came from one direction, that it would have a directionality, that it wouldn't be a circle. But what's really going on is that it compresses the Earth, and it's actually the shock release that's creating the crater. So it's actually an explosion. And one of the really interesting things also about this science was that it was evolving kind of at the same time nuclear weapons were evolving. It's not a coincidence that Luis Alvarez, the father of Walter Alvarez, who we'll get to the dinosaur story, but he had actually been part of the Los Alamos project. And a lot of the things that we know about how these things form, like what kind of structures there would be, like there's shock ports, for example, which couldn't be formed only from nuclear bombs or from impact. So it's really shock things so it's not a coincidence that we know about these things together.
That's why Tunguska, the trees are all flattened in a sort of a circular way because it exploded above, right?
Well, that's a little different because that wasn't an impact. So it's not a crater. That was just the fact that it exploded in the atmosphere.
So, but the Barringer one, the meteor crater in Arizona, it actually hit the dirt.
Right, and there's an
Okay.
actual genuine crater there. And there's a lot known about crater formation, what the shape will be, what there's this overturned rim, because that's, you want to be able to tell the difference between impact craters and volcanic craters. And so there's a lot that we know about it now to be able to establish which is which.
So if we didn't have an atmosphere and weather and so forth,
We've got a lot more stuff. hidden.
this would look like the moon, right? We would look like
Well,
the moon?
no, actually it's interesting because there's a couple of reasons we don't look. But one is we have a very active planet. We have a lot of geological activity, so stuff gets washed out. In fact, most of the craters on the moon. I mean, so this all came up during the time, which we'll talk about, for the impact hypothesis for the demise of the dinosaurs and a lot of other stuff. But you might think, well, of course things are hitting. You look at the moon and you see that. But actually, it turns out that most of the craters you see on the moon were from the late heavy bombardment, like 4 billion years ago. So it's not the more recent ones which are relevant to what we see, because anything from that long ago has been washed out on the Earth or
Right.
went into the ocean.
Right.
So we have many fewer craters here in part because
Right,
of that.
right. So before we get into the connection between dark matter and comets and meteors, let's go back a little bit and look at the bigger picture. How does the universe begin, and what role does dark matter have in that? What is this stuff? What's the latest on that?
Okay, so first of all, no one knows how the universe began. Anyone who's telling you they know is lying. But there are
Ben
ideas.
Carson the other day was
Sometimes they're not actually lying. Sometimes they're just really don't
Deluded.
understand it. Yeah, or deluded. Yeah, so it's hard to know sometimes. But so the Big Bang Theory, of course, tells us how the universe evolved later. And by I say later, it could be a fraction of a second after the universe started, but we don't really know how it started. But what we do know is that dark matter played a big role in structure formation. And by structure, I mean galaxies and galaxy clusters and things like that are essential to our existence. And actually, it was dark matter that led to the collapse. So basically, structure can't form until there's more energy density in matter than in radiation. Now, radiation and matter both dilute as the universe expands, but radiation dilutes a little more quickly because it redshifts. But because of dark matter, there's 5 times the amount of dark matter than ordinary matter. And I guess I should say what dark matter is. Does everyone here know what dark matter is?
well, give us the Reader's Digest condenser version.
Okay. Dark matter, there's 5 times the amount of dark matter as ordinary matter. And you might say, what distinguishes dark matter? So dark matter is matter in the sense that it interacts with gravity like matter. It gets into structures this way ordinary matter does. So it's not just uniform, it interacts with gravity like matter. But the difference is that as far as we know, it doesn't interact with light. So light just passes through it. In fact, if dark matter is made up of elementary particles as we think it is, probably billions of them are passing through every second. But you don't notice it because it's not interacting in any way that we know of other than gravity, which is a very weak force from the point of view of individual particles. So that's what dark matter is. It's just matter. In fact, it's a bad name. It could have been called transparent matter, and maybe that would be a lot more clear. It would also make it seem less evil, like it does in all the movies. But actually, it's very feeble and impotent, except when it's in very large amounts, which is what happens in the universe. So in the universe, because there's dark matter, there's 6 times the amount of matter. So matter comes to dominate the energy density sooner. And furthermore, because it's not interacting with radiation, it doesn't get washed out the way ordinary matter would if it tried to form structure. So the combination of the two means that dark matter was essential to the formation of structure as we know it in the lifetime of our universe. But ordinary matter could collapse in with it because of gravity. So actually the great thing about that is that ordinary matter, which we can see because it's light, it does emit light or absorb light, is usually in roughly the same vicinity as dark matter.
Do you figure it's there at the very beginning, or does it come into existence at some point after?
That's
the
a
beginning?
really good question, and it's a part of the research we're doing is thinking about where dark matter came from, what it is, and since we don't yet know what it is, it's not actually clear. Was it created? It could be that other things annihilated to produce dark matter, but it could be it was there from the very beginning and some of it went away. But the one interesting clue, perhaps, I mean, there's 2 interesting clues at least, just the total energy density there, but also the fact that that energy density is actually really comparable to the density of matter. It's really funny because, since the Copernican revolution, you'd think people would stop being upset every time you find it we're not central. But people get really upset that there's 5 times the amount of dark matter as ordinary matter. But actually, that's an amazingly similar amount. I mean, I do find it amazing that the matter that we're made up of is as big a fraction of the universe as it actually is. So maybe that's a clue to where it came
You say
from.
5 times, but isn't something
Energy.
like 95% of the universe is dark
So
matter? Or
there's dark
I
energy,
guess.
right?
Yeah,
So,
okay.
so
All
that
right, yeah.
so if we had slides, I would show you the standard cosmic pi. But 5% of the energy density of the universe is in ordinary matter, or atoms, made up of atoms, charged particles. About 25% is in dark matter, maybe 26, but about 25% is dark matter. And the rest of it is something called dark energy. And dark energy is not what we're talking about now. It's not matter. It's just energy spread throughout the universe uniformly. And the other interesting thing about dark energy is it doesn't dilute as the universe expands. And the way we know about dark energy, the first clue about dark energy, not the first, but the way it was discovered in a sense, was looking at trying to measure the deceleration of the expansion of the universe by looking at supernova, type 1a supernova. And it turns out that it wasn't decelerating, it was accelerating. The expansion was accelerating. And that was an argument that this dark energy, this weird stuff is out there in the universe.
Pushing, or maybe
Well,
that's not the
it's
right
actually,
word.
I mean, it's actually, maybe it sounds confusing, but it's like a negative pressure thing, which is why you can have it as the universe expands.
Negative pressure, but that pushes.
In some sense, you can
Okay.
think of it.
It's a weird way to say it, negative pressure. I think I get it. But if I recall, another way that you know it's there is you have a structure of a galaxy and the stars are rotating at a certain speed, and with just the stuff we can see.
That's how you know dark matter is there,
Right.
not dark energy,
Yeah,
but dark matter.
Yeah.
Yeah, so I haven't said how we know dark matter
Yeah.
is there yet, and that
Let's-
is one of the ways.
What's the latest on that?
There's actually a number of ways now, but one of the ways it was actually discovered was exactly what you're saying. Even if you look at the stars in our galaxy, the Milky Way galaxy, they're moving so quickly that the gravitational pull just from ordinary matter wouldn't be enough to keep them in. So it was an argument that there had to be some matter that wasn't being seen in order to make sense of the system. And you could actually look at stars even further out, and there just didn't seem to be matter there anymore, which was an argument that there is this dark matter. But there's other things too that we know about now, like dark matter bends light, which means that you look back and you see multiple images of the same object sometimes. Or there's something called the bullet cluster and other clusters like it, which look like the merging of clusters of galaxies. Clusters of galaxies are gravitationally bound systems of galaxies. And they have gas in them and they have dark matter in them, as we now know. And when they get together, when they merge, the gas gets stuck in the middle, but the dark matter goes right through. So it looks very physically like dark matter, like what you would expect from matter. It just passes through. That's not interacting a lot.
It and it leaves
Well, it's just that it's just not interacting a lot, so it just passes through, whereas the gas gets stuck in the
Right.
center.
Right. And so you have a whole chapter on the different theories of what dark matter is and,
Right.
and so forth. Which one do you prefer? And what's
I
what's
prefer
the
not
best
to state my
evidence?
preference. I like the
Yeah.
idea that I mean, I'm a model builder, so it's funny because people get confused. They're like, how can you work on things that are contradictory? I admit freely I don't know which of these models is right or if any of them are right. And one of the ways I view models is, it would be very nice if it was the solution to the problems of the universe, but it's also a way to guide experimenters when they're looking for things, because by having models, you're looking for very challenging things to find. So by having models, you have some idea of what to target, where to look.
Just on a philosophical question, when you talk about a model, and maybe it has relationship to reality, but maybe it doesn't, right? You're just building models just to run experiments. But isn't the ultimate goal to match something that's really out there?
So, and as you know, because I know you've read Knocking on Heaven's Door, I mean, there's some sense in which that's true, but there's some sense in which I much prefer sort of an effective theory point of view, which is just to say, who cares about the answer to that question? Does this work? And yes, there might be something that underlies it, but this is a model of reality at the scales that we're familiar with. We might as well think of things. I mean, look, this table seems solid, right? It's a very useful concept to think of it as a solid table. But we know it has atoms and it's mostly empty space.
Right.
That is not a very useful way of looking at it. I mean, and it is actually a solid table from our perspective at these scales. And so that doesn't mean there can't be a deeper underlying reality, but that doesn't negate the fact that it's a solid table.
Yeah. So you don't get caught up on to what extent your model is real or not. You're just running experiments.
I get caught up on to what extent my model makes correct predictions.
Okay, right. For experimental physicists, those other guys.
Right. I mean, of course, you want to know what the underlying structure is, but
Yeah.
usually you have something in mind. I mean, I like to think of my research as doing that for one thing, but also trying to find connections among measured parameters to see could these things be related. And so those relationships can be real, even if there's a further underlying physics behind it.
There's this new theory of perception called the interface theory of perception. a neuroscientist at UC Irvine. And his analogy is, imagine your laptop, your screen, and you have a little trash can. You drag a file into the trash can and empty it. If you take the back off, and there's no trash can in there, obviously, these are just icons. And so his analogy is that you're all icons in my brain. If you open my brain, you're not in there. These are just neurons firing. So it's all icons. Basically, it's not quite a solipsist, but just saying we can't really know. It's species specific. To us, this is what the world looks like. To a bat, it looks completely different. And so I always wonder but with mathematics and physics, you kind of feel like, no, it's not just some subjective thing. We really are getting to the nature of what's really there.
Right, and I actually do think that's one of the beauties of science, is that it's not caught up in our limitations in terms of our perceptions. I mean, of course, we are caught up with the limitations of what we can access, but everyone can objectively do measurements to see whether they find the same thing. And there might be some underlying, I mean, I guess one way of saying it, even in that case, if you just described it literally in terms of the neurons and where it's processed, if you really understood that well enough. I mean, all of that is true. It's just your interpretation of this as an icon is sort of where it becomes very individual. So it's trying to get, so it's funny because I do elementary particle physics. I mean, this is in cosmology. But when you do elementary particle physics, people think of it as so complex. But in some ways, what we're trying to do is get to the simplest elements. So we get around all those complications to say, what are the laws of nature that operate at a fundamental level? And sort of clear it of all the complex systems that can form. I mean, one in cosmology, sort of analogous situation is looking at the cosmic microwave background radiation, the radiation left over from the time of the Big Bang. And what's interesting about that is that you're actually looking back to the time before structure form. Because after atoms, so you start off the universe with ions, which are charged particles, but then they get together and it becomes neutral. And at that point, the radiation can come straight towards us. Before that, it was bouncing around off all these charged particles. But that means when we look at that radiation, we're looking back before structure form. So we're looking back, in some sense, to a simpler time.
That would be the 13.8 billion or whatever?
Yeah, but it's actually a little bit, yeah, right. So 400,000 years. But it's still interesting so it's 380,000 years into the evolution. So it's really pretty early on by many perspectives. But by looking at that, you can see a simpler structure. All of that stuff is going to eventually, because of density perturbations and differences in density over the sky, form all the structure that we see. But if you try to understand the detailed properties, what is dark matter and dark energy, from that you have to get around all those complications. So if you go back to the simpler time, you can learn things more directly. And as particle physicists, we're trying to do that. And so at some level, we're trying to get around that. That doesn't mean we're not interested in questions of how the brain works and things like that. But that's a layer of complexity over these fundamental physical laws.
So when I think of the universe, I think of a bubble. We're in the middle, of course. We don't know where we are.
That's the wrong way to think of it.
Yeah. Okay, I know this is the wrong way. So I want to set it up for you. So I think of the 13.8 billion years as the radius, so it's really 27.6 or whatever. But that's not right, correct? Isn't it something like 46 billion years old? No, but I'm saying this incorrectly.
Well, so I think what you're talking about is, so the 13.8 billion years sort of refers to in some sense, the time since the Big Bang. But then there's also a question of the size of the horizon, which is as far as we can see. And roughly speaking, you'd think it would be 13.8 billion years, but because space itself has expanded, it's a bit more. So I think that's what you're referring to.
Okay.
And that's what you can, so in other words, if I asked you to observe something that was 200 billion years, you just have no way of getting it. Light had no time to get here in that. But it turns out it could be a little further away than 13.8 billion years because of the acceleration and expansion.
So the look back time is 13.8.
At some level.
And that's all we can say.
Well, we can say more. I mean, we say the size of the horizon, which is how far away the light that we can see can go.
Right. Okay, so you have dark matter, and then somehow it starts to affect the shape and structure of the universe in terms
somehow
of
being
galaxies.
gravity.
Gravity, okay. And so you have galaxies filled with stars and solar systems.
Well, that has to do with other things like nuclear processes. So it's not all
Right.
that simple. I mean, so
Right.
so originally structure forms, things collapse. But after that, there's a lot of other processing that has to happen. And actually, that's one of the amazing things about looking at particle physics and nuclear physics and atomic physics, how all of that translates into the kind of stars and structure we see today. I mean, it's quite amazing.
But the initial particles that begin to condense into stars, that's just gravity pulling them together.
In the beginning, it's gravity.
Yeah. And then you get electromagnetic forces and nuclear forces.
Yeah,
and-
so they're sort of, in fact, working against each other to some extent. Where radiation is
Yeah.
trying to drive things away.
So what I want to work toward is then how does dark matter interact with white matter, whatever you call it, real matter.
Ordinary matter.
Ordinary matter.
It's all real. Through gravity, as far as we know. It could be that there are other interactions. And actually, one of the things that I and others are doing research on is by looking at detailed structure, like really looking at details of the shape of galaxies. Can you learn whether there were additional interactions between ordinary matter and dark matter? And also, were there additional interactions of dark matter with itself, which we haven't seen yet? And the other thing is that experiments that look for dark matter often require there to be a little bit of an interaction. So I can say it doesn't interact with light, but maybe there's a tiny interaction with light, and that could potentially be enough to actually detect dark matter. So people are asking that question, whether there are additional interactions, but so far, all we know is that there's an interaction through gravity.
And just so when I'm dealing with my creationist opponents, when we say, what is gravity? It's the tendency for objects to be attracted to one another. Why are objects attracted to one another? Because of gravity. It's a circular argument, but it's not really circular, right? I mean, there's really gravity that we can measure, or something like it, but there's no gravitons. So what is it that?
Well, we haven't detected a graviton yet.
Yeah.
There probably are gravitons.
Yeah.
So, I mean, what can we say? We have fundamental physical laws, and we have fundamental assumptions about what's out there in the universe. It forms a consistent story. It's not just that there's one thing that collapses. There's many things that collapse. There's many details. So you can say it's circular for that one thing if you want to. You say that's what we had to require. But then you can go see, do these laws work on other systems? And then you don't have to necessarily make it.
Yeah.
So then you have some predictive power.
Right.
So it's a bit more than that.
Yep. Right. And so then, so what we want to get to is how does dark matter?
What I don't understand is why are you attracted to creationists?
Oh, they seek me out like gravity. We're in America, so this is what we do.
I was just making a joke.
So somehow, there's the Oort cloud, there's comets and debris way out there, and so somehow dark matter tweaks one of them, and they start coming.
Well,
in.
this is our speculation.
Yeah.
So we do know about dark matter. Most dark matter is in a spherical halo around the galaxy. I mean, there's the Milky Way plane, which you probably can actually see from this house, which is kind of amazing.
You can, yes.
Yeah, it's kind of nice. So there's the Milky Way plane, but then around it is a spherical halo. Now, a good question, which will be relevant, is why is there a Milky Way plane? Why isn't ordinary matter also in a spherical halo? And that's because ordinary matter radiates. It's precisely because of the interaction with light. So it can radiate, and because it can radiate, it loses energy. As it loses energy, it collapses. So it collapses into the Milky Way plane. So the structure of our galaxy is that there's a Milky Way plane and the spherical halo of dark matter around it, and the Milky Way plane is there because it radiates, because ordinary matter radiates. So we did an additional speculation over and above the dark matter that's there in the halo. And it doesn't actually sound like that massive a speculation. We said, so we know ordinary matter has all sorts of different particles. So we said maybe in the dark matter sector too, there's more than one type of particle. And in particular, maybe some small fraction of the dark matter, maybe 5%, has its own interaction. And in fact, it has its own light. So just the way dark matter doesn't experience the light from ordinary matter, maybe dark matter has its own light that ordinary matter doesn't experience. I like to call it dark light. So dark.
It's a wine too.
Even better. So dark matter, say, has its own light, but it's only this small fraction. So you still have the spherical halo of the rest of it, the 95%. But then this form of dark matter could also form a disk. And the other interesting thing about it is if the dark matter particle of which it's made is heavier than a proton, then that disk will be narrower than the disk of the Milky Way.
So I'm just picturing a plate or a frisbee or whatever, and you're talking about the halo is sort of around the middle of it, right?
So, well, it's really around the whole thing.
The whole thing.
Yeah, the halo's enormous. And then there's a plane of the Milky Way inside.
Hundreds of thousands of light years in
a couple
diameter.
hundred thousand, yeah.
Oh, okay, all right.
So, and within that is the Milky Way plane. And then there's perhaps a thin disk of dark matter within the Milky Way plane. And it's within it because the gravity would align the two. So our picture, so the first thing to know, and again, this is speculation, but what's interesting about it, I mean, I'm going to tell you the dinosaur story in a minute, but even aside from that, there are actual measurements that could be done to see whether this exists. And those measurements have to do with the fact that you can measure the motion of stars in our galaxy as they go up and down through the Milky Way plane. And if there's going to be an additional gravitational force that comes from this dark disk, you can actually detect it if you have enough measurements and precise enough measurements. And one of the really great things when we were doing this research was that we did this research in the summer a couple of years ago. That very fall, a satellite called the Gaia satellite was set to launch from the European Space Agency. And what that satellite is doing is measuring the positions and velocities of 1 billion stars in the Milky Way. So it's exactly the measurement that we would want to see whether or not this disk exists.
1 billion stars? How does
Yeah.
it do that? Carefully.
Yeah, it's a satellite. Yeah, exactly. Carefully. But that's its goal. So now we have this picture where there's maybe this disk. So then the question is, how does it eventually connect to dinosaurs and their
One
demise?
quick question before you do that. So
Sure.
the disk of the galaxies like this, and in your book you said our sun, our solar system, is going through it, not like this, but in waves. It's sort
Right.
of wobbling. What would cause it to go up and then down and then up and then?
It's just that there's no friction, so it just has some amplitude and it hasn't slowed down. So it's going. So the picture is the solar system goes around the galaxy every 240 million years, and as it does so, it bobs slightly up and down through the plane of the Milky Way. And it's just there's not enough friction, so it's just nothing slowing it down.
But why would
it's-
it bob? I mean,
There's a restoring force, so if it went up, so it goes up, but then there's the gravitational pull of the disk itself,
the disk
which wants
itself.
it to
Okay,
come
I
back.
see. All right.
And that's an important point because how quickly it does that is determined by how much mass is in the disk. So if there was just ordinary matter, that would happen about every 55 to 60 million years, something like that. But if there's a dark disk, it can happen more frequently, and that was important for our story.
And this is how you found the periodicity of
Well, we
these-
found that, so what we tried to do, so there's actually some evidence. It's not very strong, so don't go home being confident of this, but it's something we want to know as scientists. There seems to be some marginal evidence that large impacts, as measured by large craters, happen on a periodic basis of around 30, 35 million years. So as you were saying, I mean, stuff hits us all the time. There's asteroids, they hit a lot. So a lot of stuff is random. But if you look at the biggest stuff, maybe there's a separate population that's causing that actually hits on a periodic basis. And you know, it's really great. You can go look at the Earth Impact Database on the web. It lists every impact crater that's been found, their size and their age. It's a fantastic resource. And so we use that to see whether or not this happened on a periodic basis. And having a model, namely our dark disk model in the Milky Way, we were able to make predictions about what would happen. And we actually found that there was marginal evidence, again, not incredibly strong, that this was true. That if you really put in the fact that put in the data about the craters, you find that it favors a dark disk, and it favors it with certain parameters, certain thickness and certain density, surface density. And hopefully the Gaia satellite can measure, first of all, does this disk exist at all? And if it does, what are its parameters? So now we have a picture where the solar system's going around, it's going up and down through the Milky Way. Now, why do I say there would be periodic craters from this or impacts? And the reason is there's something called the Oort cloud. So there's, the solar system has planets, it has asteroids, the source of asteroids being asteroid belt and other places. There's the Kuiper belt you might have heard of, and the scattered disk, which is a source of short period comets. But much, much farther away, thousands of times farther away than the Earth is from the sun, is something called the Oort cloud, which is a bunch of icy bodies that could become long period comets. And so these icy bodies are frozen. If they get close enough to the sun, they get heated up. And when they get heated up, the volatiles can form a tail. So they can be gas and dust tails. And that's what can form long period comets. So this stuff is really far away. But the fact that it's really far away means that it's weakly bound. It's weakly bound to the sun because, as you know, Newton's law tells you it goes like 1 over r squared, 1 over distance squared. So this stuff is weakly bound.
So they're just
which
barely hanging on out there.
I mean, it's
And they're
a little
moving
bit,
really slow, right?
well, not that slow because they have to cover a large distance. But so if anything kicks it a little bit, it could potentially get dislodged out of the orbit. And so if you have this dark disk and it goes through, the gravitational tidal force can be enough to potentially dislodge some of these, and it would happen on this periodic basis. So now our picture is that as the sun goes around, it goes through the disk, and on a period of about 32 million years, comets can get dislodged. And it turns out that the KT, now known as KPG extinction, we can talk about the terminology in a minute, which killed off the dinosaurs and 3/4 of the species on the planet, happened 66 million years ago. So if we went through around 2 million years ago in the period's 32 million years, it could be that this potential, the impact, and we do know it's an impact, and we could talk about the evidence for that, the impact that caused that extinction was triggered by dark matter. So that's
what about the
title.
other 5 major extinctions?
Yeah, so there were 4 other major extinctions that we know about. And originally, people were trying to explain periodic extinctions, but there's many different causes for extinction, and we only understand it to some extent. One of the really interesting ones, so it's very interesting, so the statistics, you just have this fossil record, and you look into it, and you find that there were 5 major mass extinctions over the Phanerozoic, which is about 500 million years. And that's really where like half, 2/3 of the species on the planet disappeared. So that's major. That is a major resetting of evolution. Evolution is not always what's explaining what's going on. It's not, in other words, it's not always a slow process. I mean, that is a major resetting. One of them was caused by impact, the most recent one. But there's one, say, 250 million years ago, known as Permian-Triassic, where 95%, it was the most devastating, 95% of the species disappeared. And we don't know what caused it, but it looks like there was a lot of carbon dioxide in the atmosphere. It looks like a lot of the conditions were similar, dead zones, acidity in the ocean, a lot similar to things that are happening today. And as you know, there is some evidence that we might be going through a 6th extinction now of man-made origin. And by looking at these, maybe we'll learn something about the conditions that lead to extinctions.
So do these other ones match your periodicity of your dark matter?
There's some marginal evidence for some minor extinctions, and I talk about the ones, but the evidence isn't that strong. I mean, there's one, Devonian, that does look like there were some impacts involved. It looked like a bunch of, but it's not really clear what's going on there.
But you don't need that because you have the other periodic impacts that didn't necessarily.
Well,
cause
so
this.
we don't try to explain periodic extinctions. We try to explain periodic impacts, which is closer to physics. And just for extinctions, there's so many factors that can come in. I mean, it's just coincidental, perhaps, but one of them does seem, or it's real that the one we're talking about, where we do know it's an impact, seems to correspond to our period, which is very nice.
So the dark matter can interact with this Oort cloud because it's so weakly bound to the sun.
I mean, exactly. It's interacting with everything, but it could have a more dramatic effect there because it can trigger dislodging a comet from its orbit.
And how confident are you that the dark matter caused the demise of the dinosaurs?
I'm not confident at all. I'm confident that this is really great science to be doing. It's really fun. I mean, for me, it was like a great learning opportunity. I mean, one of the things that's interesting, even if independent of the dinosaur story, is how astronomical this research became. I mean, usually I'm doing things that are more particle physics or even cosmology oriented, but here you really have to understand the detailed structures of galaxies. It really was more nitty-gritty of what's going on in the guts of the galaxy. And the connection to the other things was also really interesting to study. I mean, I would not say I'm really confident that this is all right, but I definitely think it's worth, when they do these measurements, that guy does these measurements, it's again important to have models in mind, because if you don't have models in mind, you won't find it. I mean, you look at the literature and they'll say things like, there's no need for a dark disk. It fits with ordinary matter. But that doesn't tell us the answer. That just, I mean, we wouldn't have found the Higgs boson right away if we thought that way. Because you just have to know what distinguishes the actual detailed physics.
One of the things I liked about your book was the history that you included in there, and I was surprised at how late in the game it was. We had the idea that there could be astronomical linkages to mass extinctions. I mean, the Alvarez thing was like late 80s, right?
I know, it's crazy, right? And it met with a lot of resistance.
Right.
And even just the whole idea of things hitting the Earth, that there were impacts.
Wasn't it like in the 19th century, they go, those madmen who think things are falling from the sky?
But it wasn't just madmen, it was like farmers, people who were out there that actually saw the stuff fall. But the scientists didn't really believe them.
Right.
And in fairness, I mean, farmers saw a lot of crazy stuff, as you know, too. So they were skeptical. But then there happened to be an asteroid fall right, near the Science Institute in Siena, I believe, and people began to take it seriously. Yeah, I know, it was very lucky, actually.
But it was Eugene Levy that was really promoting this, the impact idea, and he was not initially receptive.
Well, it's you really need a lot of evidence. In a way, I talk about a lot of the debate that happened. In a way, it was really great for science that there was this debate, because it meant that they really had to find a lot of evidence. I mean, when I started working on this book, I don't know about you, but I'd heard about the impact hypothesis. I didn't realize what solid footing it's on. I mean, it could be, I mean, now there's evidence that excess volcanic activity happened around the same time. But even if that's true, it very likely was triggered by the same impact that caused a lot of other damage.
Impact.
Right, so the impact that we're talking about, and that whole story is just great. You know, just first of all, how they found, why they thought it was an impact, then what the evidence was that was an impact, and then the amazing thing that they actually were able to find the crater that corresponded to this, because the odds were against that, right? Most of the Earth is covered by ocean, so any individual impact, you're not likely to leave a record. On top of that, the evidence for an impact, the first evidence, maybe some of you have heard about the iridium layer that was all over the globe that indicated something had come from outer space. But if it's all over the globe, where do you look for it? So they were kind of lucky because the thing landed on a continental shelf. So there was a tsunami, but it was localized. So by finding evidence for a tsunami in Texas and in Haiti, they could localize the region, know roughly where it should be. But they still didn't know. They looked at the list of stuff and it still didn't seem to match. But then independently of this, Pemex, a Mexican oil company, was looking for oil. They were doing surveillance and geological surveying and magnetic also, and they found a circular structure in the Yucatan, under the water. But that wasn't really of interest to them because they were looking for oil. So that kind of information was considered proprietary at first.
They had a different model.
Yeah, but they just didn't care.
A business model.
Yeah, just didn't care. And but then some of the geologists actually did get permission to talk about it. But these two groups weren't really talking to each other. And actually a reporter seems to be the one who connected them and said, you know, this oil company has actually found, these geologists at the oil company have found this. So it took a long time before they actually found it. But the great thing about finding the crater is then you could do detailed measurements of when the impact happened and see how it corresponded to when the impact happened. At this point, the dating has been done to within 20,000 years,
Wow.
which is incredible for something 66 million years
What
ago.
did they figure the size of the impactor was?
The impactor itself is about 10 to 15 kilometers big, moving greater than 20 kilometers per second speed. So it had a huge influence.
That's
It's a
faster
big
than a
thing.
bullet.
Well, it's 500 times faster than a car on the
Yeah,
freeway.
yeah.
Actually, a lot more faster than cars on the freeway here. But
Faster than my Tesla? No.
yeah.
Well, this is interesting to me also in reading your book about paradigm shifts. I mean, in hindsight, you go, well, that was the right one, so they should have seen it years before. But, you know, there's lots of alternative theories of physics. I'm sure people send you these papers that they write on the weekends, and they promise to share the Nobel Prize with you if you'll just help them with the math. I get those too. You know, so there's probably a good reason why science is relatively conservative, and it's probably good that it takes a while.
Right,
And that there's pushback and
I think that's right. I
skepticism.
mean, basically, if there's a standard explanation, it's probably right. And to actually show something new is true, you really want to have strong evidence for it. So I do think that's fair. I mean, I do think people should listen to the evidence. You know, if you just ignore the evidence, that's not a good thing. But if you actually present the evidence and evaluate it, that's really good. And a related historical thing is, you know, just for all of science and many other things in our society today too, is sort of the speed at which they happen. I mean, in some of the debates, the debate over evolution itself and life, you know, has to do with, do things happen slowly or do they happen quickly? I mean, Darwin's great insight in some ways was to think things happen slowly. Cuvier realized that extinctions could happen, and he thought everything was catastrophic. And what we now know is that sometimes it's slow and sometimes it's fast. Just like the evolution of the universe in the beginning is very fast through cosmological inflation, and later on it's the Big Bang Theory, which is slower. So I think, you know, putting together these two very different ways of thinking about how things are changing is also really important.
You ever heard of these guys, the electric universe theory people? Oh, you're
Oh wait,
fortunate.
I get email from them.
Yes, you do. Yes, you do. I get email. Well, they actually invited me to speak at their conference a couple of months ago on the difference between science and pseudoscience. So I said, well, I hate to tell you this, but that's you. You know, by way of example.
And what did they say?
Well, they weren't too happy about hearing this. But
Did they have you speak?
Oh yeah, I spoke,
Okay.
and you know, explained. You know, 'cause there was a talk by this guy, self-taught mathematician. You know, Einstein was completely wrong, and he had an hour's worth of slides with formulas that I had no clue.
Actually,
what he
one
was
of the
talking
really
about.
funny things about dark matter is that people would rather believe that Einstein's equations get modified than that dark matter exists. Whereas dark matter, it's
Really?
so much more modest an assumption. I mean, not everyone, obviously, but there's people that are like, how do you know there's dark matter? Maybe Einstein's equations are wrong. But that's much more radical
Right.
to think that the equations are wrong than to think that there's a form of matter we don't detect, given that we know exactly why we wouldn't detect it.
Right. Well, part of my answer was that there's a reason Einstein was Time's person of the century, because he's been tested and tested and tested, on 100 years of thousands of physicists that have tested his equations. What are the chances that this one guy, figured out he's wrong, and all these other people, So me not knowing anything about this subject, I'm reasonably confident that people like you are competitive enough that if he was wrong, you would have figured it out by now. So I can have some,
Well,
faith,
in
but confidence.
fairness, it could break down in a regime we haven't tested before. I mean,
What does that mean, regime?
distances or energies. I mean, we've tested things
Oh,
only
okay,
over
all
a
right,
certain
all right.
range, and it could be that it's actually going to be an effective theory. And in some sense, that's what string theory would say, that it's an effective theory, that it works only over a certain range, and at some point, you're going to find it breaking down.
Well, then
And
that's like
also consistent.
so Newton's not wrong; he's just restricted.
Exactly,
Yeah, okay,
and that's
all right.
one of the big
Okay,
ideas
all
in
right,
physics,
well,
that
all
people,
right.
it's really important for people to understand that, because they get very upset that things are wrong, but they're not wrong. They're
Right.
just, they're approximations.
Well, so part of the problem that outsiders have is they don't know how the inside process works. It's conservative for a reason, because most new ideas that people come up with are wrong. So in reading your book, it's like you and your collaborator, I forget his name.
Matthew Reese.
Yeah, Matthew. You could just almost hear the ideas bouncing back. Let's try that. Let's try that. No.
Right.
No. And that's, so outsiders don't see all the no's and the rejections and that we were wrong, and then you finally get the book. Okay, well.
Well, I think I put in more of that than
Yeah.
most people do.
Yes, you did,
sort of
yeah.
the ways that
Yeah.
these ideas really come
Yeah.
about.
So, so just a couple of just sort of related questions before we turn it over to the audience. What's your confidence on multiverses of these days, since you've written those other
Again,
books?
this is, it's funny. I joke that, like, why are we caring about multiverses when we
Yeah.
want? Let's look at the multiverse of matter that we have right under our noses.
Yeah.
I mean, the thing about multiverses is that, we probably can't test the idea. So I think it's very likely there are other universes, and I think it's very likely we'll never know about them. Okay, let's move on.
Okay.
You know?
Right. What about this star KIC such
I don't
and
know
such?
anything about
You don't know
that.
anything about that? Okay. Well, it may have an alien structures blocking the light. Probably not.
Yeah, it's probably a statistical fluke.
Yeah. Or it could be some of this debris. It could be an Oort cloud with holes in it or something that blocks the light, and it's a light fluctuating star more than most. But well, I was on a radio show with Art Bell recently, and this came up. This star, and he said. Well, I have a NASA insider who tells me. I'm like, oh, well, I have NASA insiders too, and they've never told me. It's like, well, I can't tell you who it is. It's top secret. Okay. More than 50% probability that the dimming of this star's light by 20% is not natural but artificial, like a Dyson sphere giant solar panel.
And also, a lot of problem with those kind of reasonings too is, I don't know about this particular one, is, unlikely things do happen. I mean, there's so many unlikely. You have to take into account the fact that there's a lot of possibilities for what unlikely things could happen. So any individual one is unlikely, but
Yes.
the idea that nothing unlikely happened is also very unlikely.
That's good. That's a good way. I'm going to use that. Well, anyway, so but then immediately the host. This is how it goes in the sort of public communication of science. He's greater than 50% probability it's aliens, and then the radio host goes, "Well, what are they like?" In other words, people just take that step that it might be alien. Oh, okay, who are they? It's 1,500 light years away. It's going to be 3,000 years before we'd even get an answer. How are you, or what are you?
Well, I think that shows unusual curiosity about foreign cultures.
Yes. And so where are you these days with the science and religion debate? You're an atheist or a non-believer. And this is this. To what extent can we get along with the other side? Should we, in the sort of Dawkins way, should we be more confrontational and try to put an end to this, or just, live and let live and keep things separate?
And as as you've read Knocking on Heaven's Door, I have a couple of chapters, and I mean, I think for many people, religion is like a personal or sociological phenomena. It's a family. If people want, I'm not going to tell people how they should live their lives, but they shouldn't tell me how to live mine either. And I think, as long as you don't come up against science, I think it's fine. People can do what they want. I think it is important to recognize what science tells us and why we believe it. And, and it is odd sometimes, because even if you say things like, well, I rely on religion for moral choices. I mean, but we sort of know that even if we don't know how it works, we know that everything that happens in our brain relies on physical processes. So then do you really believe there's an external agent out there who's tweaking things as this happens? And you can believe it, but it doesn't really add anything to the discussion because everything we do is going to be the same science. Or you might believe it started things in the first place. And again, it won't change anything we do. So as a practical matter, I think it's important. I just think just as a practical matter, it is important for people to listen to each other. But I also think it's important to let science progress.
But Vic Stenger made this point in his book that God is a testable hypothesis. That is, if there is a deity, the universe should show certain signs, or it should be structured in such a way. And everything we've measured, mostly physics in his field, shows that there probably is no God. So could you not say it? In terms of like different models, the God model is less likely than the no God model, or something like that?
This is the problem that people get into when they argue with believers. I mean, believers are not relying on logic. They're relying on faith. You can't argue with that.
Right.
It's faith. So, you can convince yourself that God is unlikely to exist. That doesn't mean you're going to convince a believer who relies on faith that God doesn't exist.
I have experience with that, yes.
But I'm saying, I'm not even sure. I mean, you have to first make the argument that this is not the way you're approaching. I mean, you have to understand that the way you're trying to understand the world is not necessarily the same. And I think there are interesting questions why people are mistrustful of science and why they don't feel as powerful in the face of science. I mean, you and I feel more powerful. We feel like science can help us understand the world. It can help us solve problems, but not everyone thinks that. So I think a more useful tact would be to understand, why doesn't everyone believe that? Why do people feel alienated from the progress we're making with science, and address those issues?
Right. Well, probably something else, psychological or emotional.
But it's more than psychological. I mean, I think there's a society where not everyone feels engaged. And I think it's important that people are educated and that they're engaged. I mean, I don't know how to answer. I don't know how to answer. That was pretty funny.
It's Siri's asking you. Siri's doing the interview now. But I mean, of course, believers rarely say, well, I believe because my parents believe.
I think that was a sign of God, actually. I think that was God.
This does happen at our events, actually. We get weird stuff happening here. All right. I'm not totally closed off to it, just in case. I have a little speech prepared if there is a God, what I'm going to say. Anyway, but, just in case. But of course, believers rarely say, oh, I believe because my parents.
But then again,
believe,
everything is true about the null set.
Well, that's right. That's good. I'm going to use that too. But I'm sure they come up to you and go, well, what about the fine tuning and the Big Bang?
Well, actually, I can tell you. I mean, it's kind of funny because when I was writing this book and trying to learn about the coincidences that go into our planet, actually one of the best websites to look them all up is actually a religious website because they enumerated all the things that look coincidental that contribute to our world. And
does that give you pause, or do you think that's just the way it is?
No,
had to happen in some universe.
I think we think about things incorrectly, that we feel like we're predicting. I mean, this is where we ended up. And it is amazing the number of circumstances that happen to give rise to life, but we don't really understand what it is yet. But it's, I think as a physicist, it just makes you think about what these parameters are and what the consequences are. But I think we have a little bit too much hubris about our understanding. Like, if we didn't actually have this example of life, it's not like we would have predicted it would exist or we understand it to that extent. So I think at this point, I'm just looking at it as gathering information.
Right. And then finally, just because of this movement sweeping across the country of student protesting at colleges and universities about the lack of diversity and so forth, sit-ins and whatnot. I don't know if this has happened at Harvard yet. I think there's been a few.
I was away, but there was one,
little things. And you're the first tenured woman professor in physics at Harvard, I think.
I'm not actually the first tenured theorist.
Theorist, yeah. Well, anyway, but the point is it better now for women in math and science than it was, say, when you were an undergraduate? How have things progressed and changed? How much further do we need to go?
I think that it has a lot farther to go. Just if you just look at the numbers, it's funny because we sort of start by asking about in science, but really, I mean, it's all a society. It's not like, I think of it like, you have this like tree that's ill, and you try to solve it by looking at, the tiny little branch. I mean, it's maybe more visible that branch is dead, but it's part of a bigger question of how we treat gender issues in society as a whole. So I don't know that I have all the answers.
But like in biology, there's more women PhDs than men now. Medicine, more.
What about professors, though?
I'm not sure about professors. I think it's still not
Well, there you
not
have it.
50-50, yeah.
Yeah.
So, and is that just we have a ways to go because of momentum takes a while? Or is there still institutional sexism, racism, and so forth in the academy? We often think of the academy as a very liberal place to be.
You're trying to
But
get me in
maybe
trouble.
not.
You're
No,
trying
no,
to get
just,
me. There is sexism in the
yeah,
academy. There's
okay.
no question about it.
There is,
Yeah.
okay. All right. What do we do about this? Just keep pushing.
I mean, look, you just do what you do. I mean, you focus on your research. You focus
Right.
on the things you do. I mean, I think, I think, a lot of these things are hard to see. I mean, one of the things that happens in academia is basically, to some first approximation, everyone's kind of miserable, right? They all feel like they're not getting a fair deal.
All
like the
academics are
idea
miserable.
that there's actually a difference in, sort of question of the degree and what's going on and things like that. So, I mean, you see it in all sorts of places.
Yeah. And then finally, just on the nature-nurture question, because I was interested in reading about your sister, Dana Randall, is professor of theoretical computer science at Georgia Tech, interested in using algorithms for counting problems using Markov chains. My old job. Obviously your parents, good genes, good parents, good upbringing. What was it that led you and your sister to get into the sciences?
Well, my sister is 4.5 years younger, so she gets mad at me because people ask me, were there any scientists in your family? And I say no. and she says yes, because there's a big difference between having a sister who's, So when I was doing it, there were not scientists in our family. I mean, education was valued, but it was something that at some point I decided I wanted to do.
I mean, but your parents weren't scientists, or they didn't give
weren't
you science
scientists.
books to read or whatever?
I mean, they encouraged us, my mother especially encouraged me to do well in math, but, and I certainly was never told that you shouldn't be doing well in it. I was good at it.
I remember Sally Ride talking about girls leaving math and science in I think eighth grade was sort of the tipping point when they bail out of these classes. I don't know if that's getting better or what the solution to that is.
I think there's still a real problem. But again, this is not what I'm
Yeah,
dealing with.
yeah,
I don't see this.
Yeah, I understand. Right. Well, let's turn it over to the salon and see if you have any questions or what you'd like to converse about. Yes?
Very basically, Dr. Randall, how do you visualize the universe?
How do you visualize the universe?
It's interesting. I'm not sure. It's funny. It's an interesting thing when I'm writing books because a lot of people think very visually. I'm not sure I think that visually. I think conceptually, but I don't know that I need a picture because I feel like a picture sometimes won't even tie you down too much. Like it's better. So, I mean, I'll visualize certain processes or certain features, certain connections, but I don't think I very often sit down and visualize the universe as a whole. Yeah.
It's not bounded.
And certainly, I don't think of it as bounded. Yes, I think it's. And I actually talk in the beginning about why I think it's more likely to be infinite. That's just me.
Along that same line, you were talking about that the dark matter would be kind of like a sphere around the Milky Way. Is then the idea that the dark matter is kind of following wherever the regular matter is?
Well, it's actually the opposite, which is what I was trying to explain earlier. So dark matter will collapse into structure, and then ordinary matter kind of comes along for the ride and hitchhikes. And then after that, the ordinary matter collapses and forms a disk and forms all sorts of other structure. But really, dark matter, in some sense, was essential to initiating this, especially something on the size of a galaxy or smaller.
It floats away or it stays there? Or is it staying?
No, so dark matter, it's all moving around. It's just gravitationally balanced. The stuff is moving, but it's in a roughly spherical structure, whereas the Milky Way, again, stuff is moving, but it's more or less moving in a plane.
Yes?
Is there like a one-to-one correspondence between dark matter and the matter that we see, or is it?
Well, 5 to 1, right? Or
So, well, first, right. So actually, we don't know the answer in some sense, in the following sense. There's this interesting question of why the amount of dark matter and ordinary matter are so comparable. I mean, you might think there's a lot more dark matter, but really it's comparable. It could have been 10 trillion times. It could have been an enormous amount different or 10 trillion times less. So it's rarely comparable. So it's possible that there is some sort of correspondence like that, that maybe, so ordinary matter, so there's actually a mystery about ordinary matter, which you often don't hear about. But the question is, why is there matter and not antimatter? Because you would have expected, and if there were equal amounts of matter and antimatter, it would have annihilated away. It would be turned into energy, and we'd have hardly any matter left. So we know that sometime in the evolution of the universe, for whatever reason, there's more matter than antimatter. So some people try to explain that the fact that the amounts are comparable, the energies are comparable in dark matter, by a model
where there's a dark matter, anti-dark matter asymmetry. And in that case, the numbers would be related. In most cases, it's no. But in this case, there might be some connection like that.
There is no anti-dark matter?
We actually don't know. We actually don't know. We don't know, and dark matter might be its own antiparticle. We don't know yet.
Cool.
Although there are a lot of people who are anti-dark matter.
Lisa, do you do numerical modeling of the dynamics of the...
I have students and graduate students who help me out with that. Yeah, but there is modeling going on.
Does dark matter couple in an angular momentum sense with ordinary matter?
Yeah, I mean,
So the galaxy has
there's
angular momentum.
right. The force is gravity, but yes, the dark matter. If there is a dark matter disk, then it'll be rotating the same way as ordinary matter.
But you said there was a halo. Wouldn't
Yeah.
that couple through angular momentum into a spinning halo, which would then flatten it?
It's slightly flattened. It's not exactly spherical. It is slightly flattened.
Good one back here. Yeah.
Yeah, okay, I actually have
Oh, he's reading the question.
No, don't read it. Don't read anything like just.
This is about the dark matter, light matter. The assumption is that the normal matter that we are made of and we are used to is a collection of particles, and some of those particles are called fermions, and the particles that they interact between the fermions are called bosons, right? Now the
Not quite.
supposition is something like that, right?
Actually, the forces can be mediated by bosons. Matter can, in principle, be fermions or bosons. So we don't know which dark matter is.
Okay, but the matter and the forces are a collection of particles, and the supposition is that dark matter is another collection of particles that also will be something like the fermions and the bosons. It will have the same structure. Now the question will be, it could be that between the two groups, the reason that they are not interacting is that there is, like one particle that is missing, an hypothetical particle that could exist, or maybe it existed.
Right, so there could be ways it interacts other than light. I mean, there could be some other connection. And that's when they're looking for dark matter. It could, if there was some other kind of force that could also lead to detection. So there are constraints on that because we have not yet detected dark matter. But it is a possibility that there are other ways that these things could interact.
Yeah, now the question it will be if something like the LHC could generate, synthesize that particle at least for a small fraction of time, then all of a sudden we will see that all our universe, all the particles on this on what we are used to, will start interacting in some way with that other part of the universe that is the dark matter, and then all the interaction that we see with the particles here suddenly will start to change, maybe.
No, so the LHC isn't changing anything. It's just detecting what's already there. So whatever it's been happening has been happening. The question is, in addition to gravity, is there some tiny interaction between ordinary matter and dark matter? And we can figure out what the influence of that would be. And on the whole, for the things that we've talked about so far, it wouldn't change things very much because it would have to be very, very tiny.
You're an LHC insider. Is there anything big coming up we should be looking forward to?
It would be nice, but I don't know.
It's hard to say. Yeah.
I
okay.
mean, it's a limited range of energy that they're accessing now, but they certainly are doing hard
Right.
work to try to see what's there.
I think you had a question.
I'm wondering, so there was this impact, and it caused a mass extinction. Why?
So I like to joke that every movie disaster scenario except for the zombie apocalypse happens. It's like really, there's fires, there's tsunamis, there's earthquakes, there's dust goes into the air, there's acid rain. I mean, but really every bad thing that can happen when this happens. I mean, and so there were probably fires in the beginning. There was definitely certainly gas and stuff that went out. There really were tsunamis. So and then how it happened in detail, we don't necessarily know. And it might have even triggered excess volcanic activity, which would have put more carbon dioxide in the atmosphere. But basically, a lot of the stuff on the surface of the Earth probably burned. I mean, they can actually see evidence of fires from this time. It's quite amazing. Well,
Not just living.
so the stuff, right, so some of it, so hot things kind of fell down onto the Earth. It kind of went into the atmosphere and fell around. So there could have been stuff like that all over the Earth. And then there was nothing for things to eat. I mean, people think of evolution as things adapting, but a lot of the adaptation is just stuff goes and moves somewhere more compatible with but if you ruin the whole globe, then there's no place to go. So a lot of the stuff that survived seems to have been stuff that could go into the air or go underground, or stuff that ate garbage, or, it's just stuff that could survive this crazy conditions.
This was the original argument Sagan and his colleagues made about nuclear winter, that most of the humans in a global nuclear exchange would not die from radiation, but just from all the fires, and then there's lack of food and so forth. And so there's a trickle-down effect.
There's many ways to die, basically.
A million ways to die in the West, yes. Yeah.
On one of my science blogs that I check on the computer, and also I think I saw a couple of things in the news about a small galaxy on the edge of ours that has very few stars, and I think there's a significant amount of dark matter.
Right, so there are dwarf galaxies
Yeah.
which are bound, so the dwarf galaxies can be bound to another galaxy, a bigger galaxy, gravitationally. And it's a place that people look to study dark matter and study their properties and shapes and distribution of matter, because they are so heavily dark matter dominated.
Yep.
I first heard about the EPR and spooky action in college physics in the 50s. Has there been any update on that? Because it seemed to me
Still
like
true.
it's changing.
It's still true.
Yeah.
That's the spooky thing.
Well, not really. I mean, that's what basically quantum mechanics is right, and it's still right. Go figure. I mean, it's been tested to a greater extent now, but
Of course, a lot of the New Agers glom onto that as evidence that we can affect things at a distance without the normal.
yeah, I wouldn't say spooky action and distance. I mean, things start off correlated, they're still correlated, and then they're correlated.
But in terms of can people use this to read other people's minds? No.
I
Yeah.
knew you were going to say that.
Oh man, you're good.
What are some of your thoughts on the ether theory?
Ether.
Yeah.
The idea that everything's part of an electrical, interconnected energy.
I mean, the fact is, even for electromagnetic or gravitational radiation, people think there has to be some substance there, but it's not true. I mean, there's fields there which carry the influence of forces, and I think that's all I'm going to say right now.
Well, but what he's after is what you do talk about, the interconnectedness of everything. I mean, it is
but
not quite that way, but it's
I don't mean
interconnected.
in that way. And I say of the universe. I should say in the universe, because I don't think everything is connected, or at least not everything is connected in ways we test. But I think it is interesting when you think about, and it's just a different perspective, but you think about life, which relies on carbon. So first of all, carbon came from the center of stars. But on top of that, it relies on the carbon cycle. Our carbon cycle on Earth relies on plate tectonics, because it relies on stuff, as you know very well in California, going up and down into the atmosphere through geological activity. And that relies in turn on nuclear decay in the mantle, which is heating up the system. So you don't often think about it, but they're like these amazing...
Those are interconnected.
Right.
Yeah.
So it's just things like that.
Hey, when someone like your colleague Max Tegmark says the universe is mathematical, what does that mean?
Good question. Ask him.
This is not your thing, the math.
I mean, I think, there's certainly the fact that laws of mathematics in terms of physics apply, and I think it's very important to keep this effective theory in mind. I mean, I think he goes further and sort of wants to say that every mathematical structure gets realized, and again, I say whatever he wants. How are you going to test that?
Yeah, testing it. Right. Yep.
So we're assuming that laws of physics that apply to matter and energy apply to dark matter and dark energy.
Well, yeah.
But it seems like what we're doing is we're making that assumption, and then we're calculating how much, so gravity works the same way.
Well, if it weren't true, it'd mean that we don't understand what matter is. Because, by definition, matter is something that interacts with gravity like matter. What's up?
Seems like we wouldn't understand what energy is.
No, antimatter interacts with gravity like matter as well. Antimatter is just defined by the fact that it's opposite charges. So you can have, it's like an electron has a certain mass, a positron has a certain mass. They have opposite charges, but their interaction with gravity is the same.
So the laws of mathematics and quantum mechanics, all the mathematics.
Everything applies to antimatter too. Yeah. And again, we're just assuming, that is the nature of the physical laws.
Anybody up here?
People want to drink their wine.
Changing gears, are we past the tipping point on climate change? Is this too little, too late?
Are you saying should we not try to do anything about it?
No, I think we should try everything we can, but it just...
I mean, look, the climate, I'm pretty sure, will change. I mean, are we past the tipping point on the melting of the Greenland? I mean, probably not. You know, so there are some things that
I guess
at least we can delay.
Reverse the other way back. Like we really took action and really got to becoming green, say, in the next 20 years. Would then all of a sudden Greenland start forming back up very quickly, just as rapidly as it melted? I mean, sure.
I mean, it's not so simple, and you and I both know that. But still, I mean, I think there is a strong argument going forward. Can we be more cautious? And you know, and I can't predict what kind of science will happen in. You know, I mean, maybe I don't see at all how it would happen, but maybe people will figure out ways to remove carbon in ways that are economically viable. You know, more likely we'll try to do quick fixes, which could do as much damage as they do save some things. So I think the big lesson that I'd like to see people learn is we should really think about the consequences of our actions a little bit more comprehensively and not just think about the immediate impact. So, so I wish I could say that I think, you know, it will solve everything, but I also don't think it's a reason not to do anything.
Agree. To add on to that, so you talk about the acidity of the oceans. I mean, historically speaking, how bad are they now, and how bad it could be in the next 50 years compared to like where it really wiped out fish? And I know we're having problems with shellfish now, but are we really getting close to that, or is it just relative?
So this is not my field of expertise,
Yeah, okay.
so I don't want to I do know that the conditions are getting more and more similar to what happened during this massive extinction, but I actually don't know what will get wiped out.
Elizabeth Kolber's book, The Sixth Extinction, is pretty good on this.
Well, she's pretty cautious too about making claims about what will happen.
I'm all for doing everything we can.
Another solution is economics, that is changing people's incentives to act in a certain way. Carbon tax credits, for example, or just driving electric cars, or using less carbon in whatever ways we can do that. The problem is getting everybody else on board around the world that are further behind or not economically capable of doing that. If you need coal power to run your electric generators, you still have a problem there. So, but I like the economic models. That is trying to change people's behavior. There's one thing to change people's sensitivity to the environment. We should, the Greenpeace type approach. But people are just selfish. Okay, they care about next week, right? So changing their
But you are thinking more about people living here in this very nice part of the world. I think you still have to deal with the third world, and their economic incentives are different than the ones we have here.
Yes. Well, my wife's from Germany, and they get over half of their energy from they get over half of their energy in Germany from renewables.
Although they've gone in the wrong direction recently, and they started using more coal recently for economic reasons too.
I hadn't heard that.
Yeah.
Which okay.
But when they shut down the nuclear stuff,
Yes.
they needed to have something else in there.
All right.
So they've actually, yes, they've done a lot of great stuff with renewables, but it's it's tricky.
You should see all the solar panels in Northern Europe. And they have way less sun than we have. I mean, look at this. Every house here should have solar panels. And it's hard to get them, actually. It's
really?
Yeah, I have solar panels, but it took like 8 months, and inspectors and bureaucrats and paperwork, and it just went on and on and on. And even when they had it installed, ready to go, they said, you can't turn it on. Can't turn it on until the inspector comes up. All right, when's he coming? All right, well, got to make an appointment. And it was like 6 weeks before the inspector came up before I could flip the switch. And if I flipped the switch, I would be penalized. There'd be a fine on my bill. It's like, you are making this as hard as you possibly can. We got all this sunshine. Let's use it. So that's economics and bureaucracy, not just,
Yeah, one question. Now that someone keep the whole climate change stuff beside me, many times we see that we start talking about climate change, and then they focus on CO2, and then they get all green, new age, that CO2 is food for plant, that CO2 is not for climate, that CO2 will not harm us because CO2 will understand, that we human, we cannot live without our brand new car or whatever. My question would be...
Well, look, there's some truth in it. We do rely on the greenhouse.
Okay, but my question from the point of view of pure physics and chemistry, I see like the periodic table is the alphabet of the universe, so CO2 is a building block of the universe, and CO2 does what CO2 knows how to do.
So can I just interrupt for a second? So just to say, you know, this is a standard mistake people make when they discuss science at all, is, you know, it becomes like a yes and no question. I mean, CO2 is incredibly important to us. It is absolutely true. The question is, how much CO2 should we have in the atmosphere? And also, what is the rate at which we're changing it? And can we adapt to something that's that rapid? And what will be the consequences? And it's not like the planet will disappear, and it's not even like life will disappear, but life as we know it could disappear. And so we want to think about what are the consequences of these changes in terms of degree, not just in terms of a black and white thing. We don't want to eliminate carbon dioxide.
Yeah, but my point is about the structure of the universe or the structure of matter or what happened. As much as I know, CO2 will always do what CO2 knows what to do, independent where it's acting. So the idea that CO2 will something like get a conscience and understand, I don't have to trap so much light, whatever. It's more or less because
I think it's just literally a question of how much CO2 is in the atmosphere.
Yep.
It's not a question of what CO2 is thinking. It's a question of how much is there. How much is there.
So I would recommend you get our little booklet on how we know global warming is real and human cause that Don Prothero put together. Yeah.
What I want to point is that if I can find out, from the point of view of pure physics, that CO2 always does what CO2 do. It doesn't change its behavior, because it's acting on the ocean.
Okay. A statement like CO2 does what CO2 does is just kind of a meaningless statement. It's the speed, the rate at which CO2 has changed in the last 150 years that's different from every other climate change that's ever been measured. It's
so
never.
The greenhouse effect heats the planet.
Yeah.
We wouldn't have liquid water without the greenhouse effect where we live. So that's good. But then you don't want it to get that much hotter, because if you get that much hotter, the conditions we've adapted to will change.
All right, so we're going to wrap it up now. And so just one last, because this is such a beautiful book. What's next?
Research, a lot of research
right
now.
Back to your
yeah, we're doing
stuff.
some physics for a while.
Are you thinking about a future book? Another big project?
I'm just happy to be thinking about this book right now, and also other ways of getting messages out, but also doing research.
All right, so our plan now is that my staff will get out the wine and the food and all that good stuff. There's a table of books there you can get, and Lisa will gladly sign them for you, right? and then you can hang out on the balcony there, here, up there, wherever you want. There's plenty out in the street.
And you can enjoy the excessively hot weather we see.
Yes. Yeah, global warming's a hoax just because it's 85 degrees in November.
I was really debating, like in my car, like I'm actually turning on air conditioning.
Thank Lisa Randall. Congratulations on your book.
Thank you.
You're welcome. Very good. Well done. Okay, party time.
All right, great.
And we'll get you take care of that.